Hello again. We're continuing chapter 11 with 11.3. Just a heads up, 11.3 through 11.7, we're going to talk about tests of convergence, divergence of series. Tests of convergence, divergence of series. We start with the first test, the integral test. Okay. What does the integral test tell us? It says that if we have an infinite series, n equals 1 to infinity from a sub n, some preliminaries here. Of course, we can denote this by function f of n, right? But we really prefer f of x. I'm not going to use f of n. We're going to use f of x, but you know what we mean. Secondly, this function f of x must be continuous, must be positive, and must be decreasing. It can be increasing for a finite number of terms, but eventually, for infinitely many terms, it should be decreasing. And if all these conditions are fulfilled, continuity for the function, this function, of course, it's positive and it's decreasing, then here is what can happen. If the integral from 1 to infinity, of course, it doesn't have to be 1, it can be 5 or 10 or 11, it doesn't matter, but finite, right? F of x dx, if this is convergent, which is an improper integral, convergent, then the infinite series is convergent as well. Convergent. If this is divergent, the infinite series is divergent. I don't want you to assume that whenever you get a convergent improper integral, and let's say you get a number, of course, for that indefinite improper integral, then I don't want you to assume that this will equal what is called S, the sum of the series. Okay, so please do not assume that. Now, a little a recap on previous series that we looked at. So we looked at geometric series, and we said that the geometric series are convergent as long as p is less than 1. I meant to say r, of course. R is the common ratio. And we have here two formulas to remember, the Sn and the S. Sum, the nth partial sum and the entire sum. So the entire sum is a divided by 1 minus r. And the nth partial sum, remember, is a 1 minus r to the nth power, this r, common ratio, and divided by 1 minus r. Okay? So please remember these. A second one that we discussed was harmonic. And we know that this is n equals 1 to infinity, a sum, so 1 over n. So this is divergent, please remember. We also talked about telescopic series. They're multiple. And now I want to add here one more, which is the power series. And this is n equals 1 to infinity, the sum from n equals 1 to infinity to 1 over n to power p. So it is convergent when p is greater than 1 and is divergent when p is less than or equal to 1. Okay. In addition to what you just saw here, we are going to be interested in the estimate. To estimate the sum of the series and find its remainder. We're also finding the number of terms for a specific imposed error, a specific error. Okay, so the explanation for this is, as we know, the nth partial sum is a1 plus a2 plus a3 plus dot 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 plus a sub n, and it stops here. The entire sum of the series continues forever, right? So a1 plus a2 plus a3 plus dot 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 plus a sub n plus a sub n plus 1 plus dot dot dot. And when we want to determine the remainder when we approximate S, the entire sum, with a particular S sub n, with the nth partial sum. When we estimate this, which we don't know, and we estimate it with a particular partial sum. So R sub n, which is the remainder for that particular n, will be nothing else but S minus S sub n, or Sn. Okay, now, so when we talk about the integral test, for example, this sum and this sum, which one is bigger? Of course, this one is bigger. Which one is smaller? Of course, this one is smaller. So the remainder for a particular n will be found between the integral from n to infinity and the integral from n plus 1 to infinity. So this is the bigger one from f of x dx, and this is the smaller one, n plus 1 to infinity from f of x dx. Now, if we also replace Rn, the remainder for n number of terms, by S minus S sub n, or Sn, and we add Sn to both sides, here's what we get. So Sn plus the integral from n plus 1 to infinity from f of x dx is less than or equal to S, the entire sum of the series, less than or equal to Sn plus the integral from n to infinity from f of x dx. Sorry that I had to squeeze it in here. Good. So I think with all these preliminaries, now we can start looking at different examples. Okay, so this is my page 3. Okay, so let's start with number 7 on 758, and that is the sum from n equals 2 to infinity from n squared n cubed plus 1. Okay, in this problem, we're asked to use the integral test to determine whether the series is convergent or divergent. So first of all, we start by the hypothesis of the integral test. And remember, continuous, positive, decreasing. Okay, so our function is x squared over x cubed plus 1. We're going to use this technique. It's not necessary here because obviously this is a bigger number than this. The function is continuous on to infinity. It is positive on 2 to infinity, and it's decreasing on 2 to infinity. However, I just want to give you the heads up. If the decreasing part is not very clear, all we have to do is find the derivative of this function and show that it's less than 0 for any number between 2 and infinity, or for an infinite numbers between 2 and infinity, but it's increasing for a finite number of n values, in this case x, same thing. Okay, so how do we do that? Differentiate the top, multiply by the denominator. I'm using the quotient rule, and so when I differentiate the denominator, over x cubed plus 1. Again, this is a technique that is not required here because it's obvious, but sometimes we will have to use this, so I'm going to give you the heads up. So we cannot conclude this just yet. So I'm going to white it out from there. It's coming up in a minute. So we have then 2x to the fourth plus 2x minus 3x to the fourth over x cubed plus 1 to the second power. And this is negative x to the fourth plus 2x over x cubed plus 1 squared. This is definitely positive. This is tiny by comparison to negative x to the fourth. So this will be less than 0. So all three conditions required by the integral test are fulfilled. So we will continue then by applying the test. So we have the integral from 2 to infinity from x squared over x cubed plus 1 dx. We know that this is an improper integral, so we have to use the limit as t approaches infinity from 2 to t from x squared dx over x cubed plus 1. I'm going to use a simple substitution where u equals x cubed plus 1 and du equals 3x squared dx. You already, if you followed any of my examples or videos, you know for a simple number I will not solve. There is no need. It's up to you, of course. You can use any method you like. So 1/3 is outside, so we have limit as t approaches infinity. Careful now. So this is indeed du over u, but now the limits of integration, 8 plus 1 is 9, and then t cubed plus 1. So this is 1/3 limit as t approaches infinity. Natural log of u, everything is positive. There is no need for the absolute value. From 9 to t cubed plus 1. Okay, page 4. Okay, so 1/3 limit as t approaches infinity from natural log of t cubed plus 1 minus natural log 9. Obviously, it's very clear here that this approaches infinity. So then, therefore, the improper integral is not convergent. So therefore, the infinite series n equals 2 to infinity from n squared over n cubed plus 1 is divergent. This is very important by the integral test. So this sentence is mandatory at the end of each problem in which you identify the test again that was used to determine convergence or divergence. Okay, moving on to 13 on page 558. We are given 1 plus 1 over 8 plus 1 over 27 plus 1 over 64 plus 1 over 125. And the question is asking us, determine whether the series is convergent or divergent. So I'm going to look at the fact that this is 2 cubed, 3 cubed, 4 cubed, 5 cubed. So it's 1 plus 1 over 2 cubed plus 1 over 3 cubed plus 1 over 4 cubed plus 1 over 5 cubed plus dot 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 plus 1 over n cubed plus dot dot dot. So this can be replaced with this notation. Good. So they're asking us to show whether this is convergent or divergent. We are just going to state the function. Obviously, it's positive, continuous on 1 to infinity, and obviously decreasing. If you have any question about that, just find the first derivative. And you'll see it will always be negative, which means the function is always decreasing. So we apply this so that the integral test is applicable. So 1 over x to the third dx. So we have the limit as t approaches infinity. If you remember, we discussed this in the previous section, this particular series. That's why I chose it now. We already know it's convergent, but now we have a test to show that. Okay. So the integral from 1 to t from x to negative 3 dx, which is limit as t approaches infinity, x to negative 2 over, over negative 2, and this is from 1 to t, negative 1/2 outside, limit of 1 over t squared minus 1. As t approaches infinity, we know that this approaches 0, so the answer is 1/2. So the improper integral converges. Therefore, that's my page 5. Therefore, from here, so it's convergent. So we conclude that the integral from n equals, the infinite series, sum from n equals 1 to infinity from 1 over n cubed is convergent by the integral test. Please remember to add that in any time and all times. Okay, let's see how we are on time. Still good. So let's look at 15 on 758. 1/3 plus 1/7 plus 1/11 plus 1/15 plus 1/19 plus ... So I see that 3 plus 4, so we're adding 4, 7 plus 4, 11 plus 4, 15 plus 4. So it appears that this is something like 4n minus 1 plus ... So when n is 1, I get 3. When n is 2, I get 7. When n is 3, I get 11, and so on and so forth. So therefore, so this is the sum from n equals 1 to infinity from 1 over 4n minus 1. So our function f of x equals 1 over 4x minus 1. So obviously clear, it's positive from 1 to infinity. It's a continuous, of course, and it's decreasing. Again, if you have any difficulties, find f prime of x, and you'll see that this is less than 0. Good, so we are ready to apply the integral test because it's applicable. I tested, I checked all conditions or hypotheses. So from 1 to infinity, from 1 over 4x minus 1 dx. Yes, I'm going to change this into limit as t approaches infinity from 1 to t. And we use a substitution, d equals 4 dx. I'm going to change this into 4 and 1/4 in front. So 1/4 limit as t approaches infinity. The integral from 4 minus 1 is 3 to 4t minus 1 from du over u. So 1/4 limit as t approaches infinity from natural log u. Again, there is no need for the absolute value. This is always positive. From 3 to 4t minus 1. So 1/4 limit t approaches infinity. Natural log of 4t minus 1 and minus natural log 3. Good. So obviously this approaches infinity, so the answer is infinity, which means that the improper integral does not converge, is divergent. And from here we conclude that this infinite series n equals 1 to infinity from 1 over 4n minus 1 is divergent by the integral test. We continue in the next video. Thank you.